Usually, when you talk about diagnosing a problem, there's this underlying expectation of precision.
Right, yeah, like it feels like engineering or something.
Exactly. Like if you break your arm, the x-ray shows that jagged white line on the film, and the doctor just points to it and says, there it is.
Yeah, it's broken or not broken. It's a clean, visible binary. We gravitate toward things that can be categorized like that.
Right, because it's comforting to have a clear cause and a defined effect. But when you step into the world of planetary systems and look at the latest 2026 climate data, that X-ray machine is fundamentally broken.
Oh, entirely.
Huh.
We're looking at a diagnostic landscape that is just completely murky right now.
Yeah, we're trying to take the temperature of an entire planet, and the symptoms don't always show up in the linear ways we expect.
No, they really don't.
So, for you, the listener, joining this deep dive, our mission today is to cut through that murkiness. We are going to examine the physical realities of our warming world through the latest hard data.
And we'll track the domino effects as they cascade through vulnerable ecosystems and marginalized human populations.
Exactly. And then we'll explore the rigorous scientific breakthroughs attempting to build resilience. We're going from satellite measurements of global energy imbalances down to the microscopic DNA of soil.
Which sounds completely disconnected, but they actually form a single, interconnected narrative about Earth's changing systems.
They really do. And we should start right at the macro level. The latest data updates show that global warming officially hit 1.37 degrees Celsius in 2025.
Which is a highly, highly significant decimal point.
Right, because for years, the international community has fixated on the 1.5 degrees Celsius threshold as this critical guardrail.
Yeah, it's the number everyone knows.
Exactly. And hitting 1.37 tells us we aren't just approaching the guardrail, the momentum carrying us toward it is accelerating. But I think people kind of misunderstand what that momentum actually means in physical terms.
Yeah, it's not just a speedometer reading on a dashboard.
Right.
The climate system is not like a vehicle where you can simply, hit the brakes and come to a halt. We're dealing with profound thermal inertia here.
Okay, thermal inertia. Break that down for us.
So to understand this, you really have to look at the specific heat capacity of water. Oceans cover over 70% of the planet, right?
Mm-hmm.
And water requires a substantial amount of energy to raise its temperature compared to air.
Oh, sure. Like boiling a pot of water takes way longer than heating up an empty oven.
Exactly. That's a perfect analogy. So even if human-caused emissions were to drop to zero tomorrow, like completely stop, the heat already absorbed by the oceans and the atmosphere ensures that warming will continue for quite some time.
Because the heat is banked.
Right. We are locking in changes that will dictate the baseline for decades, if not centuries. The 1.37 degree mark is really just the surface expression of a much deeper accumulation of energy.
And the mechanism driving that accumulation brings us to a crucial piece of data from the recent reports, which is Earth's energy imbalance.
Yes, the energy imbalance.
The research shows this imbalance has actually doubled in recent decades. Now, conceptually, I understand that Earth's temperature is a balancing act between shortwave solar energy coming in and longwave thermal radiation going out. But how are scientists actually measuring a doubling of that imbalance? Like, how do you even measure that?
It's a triumph of satellite observation, honestly. We rely on instruments like the Ceres project, that's the clouds, and the Earth's Radiant Energy System, which fly on NASA and NOAA satellites.
Okay.
And these instruments are designed to measure both the incoming solar radiation and the outgoing thermal radiation with profound precision.
Wow.
Yeah. And for most of human civilization, that system was in relative equilibrium. The energy coming in equaled the energy going out.
But greenhouse gases act as a selective filter, right?
Precisely. They are transparent to the incoming shortwave radiation from the sun, but they are opaque to the outgoing long-wave thermal radiation trying to escape back into space. They absorb and re-radiate that heat downward. So the energy imbalance is the exact numerical difference between the solar energy entering the system and the thermal energy escaping.
Okay, so if we look at this like a financial ledger or a thermal bank account, our daily deposits of solar radiation are drastically exceeding our heat withdrawals.
Yes.
And that debt doesn't disappear. It manifests as trapped heat, forcing the entire system to warm.
That financial analogy is highly accurate, and because the imbalance has doubled, our deposits are outpacing our withdrawals at an accelerating rate.
Which is terrifying.
It is. The planet is being forced to store all that excess energy, and over 90% of that surplus heat is absorbed by the oceans.
Which leads us to the cascading effects on ocean currents and weather patterns, specifically El Niño.
Right.
The NASA satellite observations in our sources confirm a strong El Niño is underway right now. And they aren't just looking at temperature to determine this. They are looking at sea surface heights in the tropical Pacific.
Yes, through satellite altimetry.
Wait, sea surface heights, so the ocean is literally taller.
It is. As water warms, thermal expansion occurs. The water molecules become more energetic and take up more physical space, causing the sea surface to literally rise.
Oh, wow, I didn't realize it physically expanded like that.
Yeah, and by bouncing radar pulses off the ocean surface and measuring the return time, satellites can detect these slight elevations in the tropical Pacific. And those elevations are a hallmark of the vast pools of warm water driving El Niño.
Okay, but the sources point to a sort of counterintuitive twist in the long-term forecast regarding these events.
They do, yeah.
Historically, we expect a super El Niño to bring intense, distinct atmospheric disruptions. But the recent climate model research suggests that as the baseline temperature of the planet rises, future super El Niños might actually lose their distinct atmospheric punch.
That's what the models are indicating, and it really comes down to atmospheric dynamics.
Okay.
During a traditional El Niño, there's a significant temperature gradient between the unusually warm eastern Pacific and the cooler western Pacific.
Like a steep slope of temperature.
Exactly. And that stark difference in temperature is what drives the shifting winds and the heavy precipitation patterns across the globe.
Right.
However, if the surrounding ocean, the western Pacific and beyond, is already thoroughly warmed due to the baseline global temperature rising, that crucial temperature gradient basically flattens out. The difference between the two regions becomes less pronounced.
I need to challenge this framing, though.
Okay, sure.
Because when I first read that the models predict a weaker super El Niño, it almost sounds like a reprieve, like, oh good, the extreme weather won't be as bad.
Right. I can see how it sounds like that.
But if the gradient is flattening because the entire Pacific is universally hot, wouldn't that just create a permanent state of atmospheric disruption? Like, is it that the event is actually weaker, or just that our everyday baseline climate has become so consistently hot that an extreme weather event no longer stands out against the background?
It is entirely the latter, and you are totally right to challenge the framing there. It is not a reprieve at all.
Yeah, it didn't seem like good news.
No, the atmospheric disruption doesn't go away. It just stops being a distinct, periodic event. Think of it as a signal-to-noise problem.
Oh, interesting.
The noise, the baseline warming of the planet, is becoming so loud that the signal of a super El Niño is getting drowned out. The extreme heat, the shifting precipitation, the disrupted weather patterns, they become a permanent fixture of the new climate reality, rather than a cyclical event we can isolate, predict, and prepare for every 3 to 7 years.
That paints a really stark picture. And this global thermal imbalance we're discussing, it doesn't just stay trapped in the abstract realm of satellite altimetry or ocean models.
No, it manifests locally.
Right. It places severe systemic stress on the physical world. So let's look at the immediate impacts of that trapped energy, starting with the natural ice reserves, specifically the Swiss glaciers. The data states that they have prematurely exhausted their protective snow reserves.
And the timing is what makes this data point so alarming.
Right, because usually snow acts as a reflective shield. It has a high albedo. But the sources emphasize that the reserves were exhausted prematurely. Why is the timing of that depletion so critical?
Because of the solar cycle. A healthy glacier relies on its winter snow accumulation to last through the peak of the summer. Snow reflects a large percentage of incoming solar radiation back into the atmosphere.
Like wearing a white shirt on a hot day?
Exactly. But it's an exceptionally warm spring or early summer melts that snow layer away by, say, June. You expose the older, darker glacial ice underneath right when the sun is at its highest angle and the days are at their longest.
Right around the summer solstice.
Exactly. And the darker ice has a much lower albedo. Instead of reflecting the radiation, it absorbs the heat.
Oh, so it just bakes.
Yes, and this initiates a destructive feedback loop during the absolute peak of solar intensity. The more dark ice is exposed, the more heat is absorbed, and the faster the glacier undergoes severe summer melt. By exhausting their snow reserves prematurely, the Swiss glaciers have lost their armor entirely, leaving them highly vulnerable to the most intense thermal stress of the year.
And we are seeing the exact same thermal stress stripping the safety buffers away from human infrastructure at the exact same time.
We really are.
The sources detail a late June extreme heat wave affecting 100 million Europeans, pushing temperatures over 35 degrees Celsius and leading to major power outages in France.
Yeah, and the scientific community analyzed this specific event using rapid attribution research.
Okay, let's delve into that methodology for a moment. When the research concludes that this late June extreme heat would be virtually impossible without human-caused climate change, how do they actually prove that?
That's a great question.
Because weather is chaotic, right?
Right.
How do you isolate the human variable from natural weather fluctuations?
Right. So rapid attribution relies on running highly sophisticated climate models in parallel. First, scientists run models simulating the current climate, which includes all the historical greenhouse gas emissions.
Huh.
Then they run counterfactual models. So simulations of a hypothetical Earth where the Industrial Revolution never happened and atmospheric carbon dioxide remained at pre-industrial levels.
Got it.
They simulate the weather thousands of times in both scenarios. If a heat wave of this specific intensity occurs frequently in the current models, but 0 times in the counterfactual models, they can confidently conclude the event is a direct product of the altered climate.
Ah, so the baseline has shifted so far that these heat waves are no longer statistical anomalies, they are just the new expected output of the system.
Yes.
And the broader context provided in the data shows that global exposure to dangerous heat stress has climbed from 16% to 22% over the last 50 years.
Yeah, and it's driven by the intersection of rising temperatures and changing demographics. Populations are growing and urbanizing in areas most susceptible to these extremes.
Right.
And when we look at the major power outage in France during that heat wave, we see exactly how the physical environment dictates the limits of our engineering.
Right, because power grids aren't just abstract networks, they are physical materials subject to thermodynamics.
Exactly.
High heat increases electricity demand for cooling systems, sure, but it also actively degrades the supply side, right?
Precisely. High ambient temperatures reduce the efficiency of thermal power plants.
How so?
Well, nuclear reactors, for example, which provide a significant portion of France's electricity, rely on river water for cooling. If the river water is already too warm from the heat wave, or if the water levels are too low due to upstream glacial melt and drought.
Oh, because the glaciers are gone?
Right. If the water is too warm or too low, the plants have to reduce output or shut down entirely to avoid overheating or damaging the river ecosystem further down.
Wow.
Additionally, the physical transmission lines, the actual copper and aluminum wires heat up, expand, and sag. This increases resistance and decreases the amount of power they can safely carry.
The parallel is just striking to me. Whether we are looking at the exposed Swiss glaciers losing their albedo shield or the European power grid losing its cooling capacity and transmission efficiency, we are looking at systems that have been stripped of their safety buffers.
Yes, completely.
They're failing under the stress of a new thermal reality they were never designed to endure.
The protective layers, natural or engineered, are just being outpaced by the sheer volume of heat in the system.
And as those buffers fail and heat domes settle over continents, the immediate victims aren't just human systems. The biological cascades are severe, particularly for the species that are perfectly adapted to the old climate baseline.
Absolutely. The natural world relies on predictable seasonal rhythms. When you double the planet's energy imbalance, you inherently destabilize the phenology, the timing of biological events that these ecosystems depend on.
And there is a completely overlooked ecosystem mentioned in the sources, the hidden life supported by glaciers.
Yes.
We usually think of glaciers as these sterile, barren blocks of ice, but the data paints a very different picture.
It really does. Glaciers and the meltwater streams they feed host highly specialized ecosystems. We're talking about unique communities of extremophiles.
Like what kind of life?
Microbes, specific insects like the glacier stonefly, and cold water adapted organisms that have evolved over millennia to thrive in these exact, near-freezing, nutrient-poor conditions.
So what happens to them as the glaciers exhaust their snow reserves prematurely and physically disappear?
They face total catastrophic habitat loss.
Because they can't just move.
Exactly. Unlike a bird or a land mammal that might theoretically migrate to a cooler latitude, these specialized organisms are geographically trapped. Their specific environment isn't just shifting, it's vanishing.
That's devastating.
The research warns of imminent local extinctions for these glacial specialists, and this matters immensely because they form the foundational food web of these high-altitude regions.
Right.
When the microscopic foundation collapses, the effects ripple upward, altering the nutrient cycling and food availability for larger alpine species.
That concept of local extinction is expanding far beyond the high-altitude glaciers, though. The deep dive sources included a broader study looking at over 5,100 plant and animal species.
Yeah, that was a huge study.
And the data reveals that climate-driven local extinctions are becoming profoundly severe in temperate regions. Now, this challenged my assumptions.
Oh, how so?
Usually when we hear about climate-driven extinctions, public attention focuses on polar bears on melting sea ice or tropical coral reefs suffering from ocean acidification.
Right, the usual suspects.
Why are temperate zones places we usually think of as having moderate, adaptable climates suddenly showing such severe extinction markers?
The vulnerability of temperate regions really comes down to the disruption of established seasonal boundaries. Temperate species have evolved to expect a certain sequence of events.
Like winter, spring, summer, fall.
Exactly. A specific duration of winter chill required for seeds to germinate, a predictable spring thaw, a measured summer peak. They are adapted to variability, yes, but within well-defined historical limits.
So the extreme heat waves and shifting baselines are pushing them completely out of their operational bounds.
Right.
Can you give an example of how that biological cascade actually happens?
Sure, consider the phenomenon of a false spring.
Okay.
Because the overall baseline temperature is higher, a temperate forest might experience unseasonably warm temperatures in, say, late February. The trees, taking their cue from the heat, begin to bud weeks early.
Thinking spring has arrived.
Right, but the climate system is volatile. A sudden sharp freeze returns in March, killing off all the premature buds.
Oh, no.
Yeah, the tree expends its energy reserves fruitlessly. Then, a few months later, that same weakened tree is subjected to a summer heat dome with temperatures it has no genetic history of enduring.
It just can't recover.
Exactly. It's the compounding stress of these unprecedented extremes that leads to local extinction. Furthermore, the rapid pace of this change means that the geographical zones where these species can survive are shifting poleward faster than the species can physically migrate or adapt. The climate is quite literally moving out from underneath them.
It really shows that no region is insulated from the systemic changes we discussed in the first section. But it's not just wildlife struggling to adapt to these sudden shifts.
No, not at all.
Human populations are facing severe vulnerabilities, which brings us to a highly critical part of the data today,
Yes.
the human dimension and the policy blind spots that exacerbate these risks.
And the research on structural policy gaps is some of the most pressing information in the entire collection of sources, precisely because it deals with how we manage the physical realities we've just outlined.
Exactly. And to you, the listener, I want to pause and clarify our approach here. Discussing climate policy often intersects with heated political debates.
Oh, absolutely.
It can get very polarized. However, we are looking strictly at the mechanics of adaptation in this deep dive. We're reporting the findings of the researchers regarding structural policy gaps without endorsing any specific political viewpoint.
Right. We're examining policy as an engineering tool and analyzing where the data indicates that tool is failing its intended users.
The clearest example of this systemic failure comes from an article in The Conversation regarding the 1.3 billion disabled people worldwide. The researchers argue that global climate action routinely and systematically excludes this population.
And when you look at the specific failures detailed in the research, the structural oversight becomes very apparent. The researchers point to the mechanics of early warning systems and evacuation protocols.
Right. If a municipality relies solely on audio sirens to warn residents of an impending flash flood or severe storm, they have fundamentally failed the deaf and hard of hearing community.
Exactly.
The warning system functions perfectly on a technical level, but fails completely on a societal level.
And consider evacuation protocols during a wildfire or a severe heat wave. The plans often implicitly assume full physical mobility.
Right. Just walk to the shelter.
Exactly. They are drafted with the assumption that individuals can quickly walk to a designated shelter, navigate stairs if elevators are shut down due to power grids failing, or board standard emergency transport vehicles.
Which just isn't realistic for everyone.
No, and for people with physical disabilities, these standardized assumptions can be fatal. The researchers emphasize a desperate need for accessible planning. Policies cannot just be implemented from the top down without understanding the lived realities of the population.
Right.
The argument is that the disabled community must have active participation in climate policy decisions to ensure these blind spots are addressed in the design phase before a crisis hits.
The sources highlight a highly parallel issue regarding remote First Nations communities enduring extreme heat as well.
Yes, the research points out that centralized top-down directives for climate adaptation frequently fail when applied to remote indigenous populations.
Because the top-down directives are basically applying a standardized solution to a highly localized problem.
Exactly that. First Nations communities possess deep historical understandings of their local ecosystems, hydrology, and microclimates.
Right.
When policymakers attempt to impose standardized adaptation strategies from a distant capital without listening to or integrating that local knowledge, the strategies are often ineffective or even culturally disruptive.
They just don't fit the reality on the ground.
Right. The researchers argue that adaptation must be collaborative and locally informed. If a community has managed its local water resources for generations, an external policy dictating new water usage limits during a heat wave without consulting that historical knowledge is likely to fail.
It makes complete sense. And the sources tie these societal gaps together with a broader analysis of climate research as a whole. A study from the University of Cambridge looked at climate mitigation papers and found a systemic issue in academia.
Yeah, this was really revealing.
They found that policy recommendations are frequently vague, disconnected from the actual study results, or treated merely as an afterthought.
This represents a severe breakdown in the science-to-policy pipeline. Scientists are conducting rigorous, vital research on climate impacts, measuring the energy imbalance, tracking the phenological shifts in temperate forests.
Right, doing all this amazing data collection.
But if the end product is a paper where the policy application is just a vague concluding sentence like policymakers should take action, the value of that research is significantly diminished.
It doesn't actually give them a roadmap.
No, it doesn't. The experts warn that these fragmented environmental policies risk costly failures. When policies are not coordinated and directly tied to the scientific realities on the ground, they can work at cross purposes, wasting funds, and sometimes inadvertently harming the ecosystems or communities they were meant to protect.
There is a striking irony here.
Oh?
Well, in our fourth section, we discussed how climate science has the technological capability to measure sea surface heights in the Pacific Ocean down to the exact millimeter using satellites orbiting the Earth.
Right, profound precision.
Yet when we look at the policies implemented on the ground, they remain blunt instruments that completely miss a billion vulnerable people. We have millimeter precision in our data gathering, but huge structural blind spots in our application.
That is the core friction point of modern climate adaptation. Our diagnostic tools, the satellites, the rapid attribution models are unparalleled. But our treatment plans are failing to account for the complexity of the human patient.
Which perfectly sets up our final section. Having identified the stark physical realities of a 1.37-degree warming baseline and the profound policy gaps leaving communities vulnerable, we need to look at how science is attempting to bridge the gap.
Yes.
We're turning to the laboratory to explore the scientific innovations focused on re-engineering resilience.
If the overarching theme so far has been systemic stress and failing buffers, this section is really about developing entirely new tools to measure, manage, and hopefully mitigate that stress.
So let's start with a fascinating piece of laboratory engineering. The sources detail an artificial permafrost lab constructed at Penn State. They are physically simulating thawing Arctic ground indoors.
It sounds like a highly specific, almost strange endeavor, but its global implications are huge.
Yeah, explain that, because it sounds wild.
So permafrost ground that has remained completely frozen for 2 or more consecutive years covers vast stretches of the Arctic. It acts as a planetary freezer, locking away immense quantities of ancient organic matter. Dead plants, animal remains, microbes that have been frozen for millennia.
Right, and as the baseline temperature rises and the energy imbalance forces the planet to store more heat, that freezer is losing power.
Precisely. As the permafrost thaws, those long dormant microbes wake up and begin to decompose that ancient organic matter. This decomposition process releases substantial amounts of carbon dioxide and methane into the atmosphere.
Which just drives more warming.
Exactly. It creates a severe climate feedback loop. The warming causes the thawing releases greenhouse gases, which in turn causes more warming.
But why do scientists need to build an artificial permafrost environment in Pennsylvania to study this? Why not just set up sensors in the actual Arctic?
Because studying it in the field is incredibly difficult, dangerous, and subject to uncontrollable variables. You can't control the weather in the Arctic to isolate specific mechanisms.
Oh, right. You can't isolate the variables.
Exactly. By creating artificial permafrost in a controlled laboratory setting, Scientists construct highly instrumented soil columns. They can precisely manipulate temperature gradients, moisture levels, and freeze-thaw cycles.
So they can see exactly what triggers what.
Yes, they use gas chromatographs to measure the exact flux of methane and carbon dioxide under highly specific conditions. They are safely and accurately decoding these complex climate feedbacks, trying to map the exact trigger points of the feedback loop before the real-world collapse accelerates beyond our ability to model it.
They're basically building a scale model of the crisis so they can understand it. We are seeing a similar drive for precision in agricultural science, too. The sources highlight the discovery of a simpler way to measure DNA-bound phosphorus in soils.
Yes.
Now, I know phosphorus is a crucial component of fertilizer. It's essential for crop growth. But what exactly is DNA-bound phosphorus, and why was it previously so difficult to measure?
Well, phosphorus is fundamental to global agriculture, but a significant portion of it in soil isn't readily available to plants. It's tied up within organic molecules, particularly in the DNA of soil microbes and decomposing biological material.
Okay, so it's locked away.
Right. Traditionally, extracting and measuring this specific hidden reservoir of phosphorus required complex, time-consuming chemical processes that degraded the sample. It was very difficult to get an accurate accounting of how much phosphorus was actually present in the biological fraction of the soil.
So it was essentially a blank spot on our agricultural ledger.
Exactly. And you cannot effectively manage a resource if you cannot measure it. By developing a simpler, more accurate extraction and measurement technique for this DNA-bound phosphorus, scientists are unlocking a critical piece of the nutrient cycling puzzle.
Why is that so urgent right now?
As the climate changes, altering rainfall patterns, soil temperatures, and the microbial activity in the soil, understanding this fundamental fertility becomes paramount. If we can accurately map this hidden reservoir, we can develop far more sustainable agricultural management practices.
So we don't have to rely as much on artificial fertilizers.
Exactly. We can ensure we maintain crop yields without over-relying on synthetic phosphorus fertilizers, which are mined from finite reserves and have severe environmental costs when they run off into waterways.
Maintaining those crop yields is going to be vital, but the deep dive sources point out another troubling biological reality regarding our food supply.
Yes, the nutrition aspect.
It's not just about the volume of food we can grow, it's about the quality. Climate stress is actively reducing the micronutrient density in staple crops.
This is a highly concerning phenomenon known as the carbon penalty, or the dilution effect.
Okay, the dilution effect, what is that?
As atmospheric carbon dioxide increases, plants often undergo accelerated photosynthesis. They grow faster and larger.
Which sounds like a good thing initially, right? More plant matter, more food?
It sounds beneficial until you look at the nutritional profile. This accelerated carbohydrate growth does not correspond to an increased uptake of essential nutrients from the soil. The plant's root systems simply don't absorb minerals at the same accelerated rate.
Oh, I see.
The result is a dilution effect. The staple crops we rely on globally, like wheat, rice, and soybeans, become physically larger but less dense in crucial micronutrients like zinc, iron, and protein.
They're getting bigger, but fundamentally less nutritious.
Yeah, exactly.
That is a slow-moving crisis for global health, especially for populations that rely heavily on a single staple crop. But the sources also outline a technological response to this. Scientists are proposing the use of CRISPR and other genetic technologies to edit resilience and nutritional value back into our food supply.
Yes. Researchers are looking at the intricate genetic code of these staple crops to identify the specific pathways responsible for nutrient uptake, root development, and resilience to heat and drought.
And then what?
By using CRISPR, which is a highly precise genetic editing tool, they can theoretically tweak these pathways. They can encourage the plant to allocate more energy to root absorption or to maintain its nutritional density even under the stress of elevated CO2 and extreme temperatures.
I have to push back on this a little bit, though.
Okay, sure.
If we are using CRISPR to edit crops to survive 40-degree heat and elevated CO2, aren't we just treating the symptom?
In what way?
Well, I think about this like a software patch. The hardware, our climate, the atmosphere, the soil is running entirely too hot. It's degrading the output of the system. So instead of fixing the hardware, which we know from the energy imbalance data isn't happening anytime soon, we are attempting to rewrite the software, the genetics of the crops to compensate for the hostile environment.
It is absolutely an adaptation to a hostile environment rather than a mitigation of the root cause. You are correct that it is a software patch for failing hardware.
Right.
We are utilizing advanced biotechnology to code resilience directly into the biology of our food systems. It's an aggressive adaptation strategy born out of necessity because the structural policy gaps we discussed earlier have failed to cool the hardware down.
Which brings us to the end of our journey today. We've covered a huge amount of ground.
We really have.
We started with the raw planetary data, the milestone of a 1.37 degrees Celsius warming baseline, and a doubled energy imbalance locking profound heat into our oceans. We tracked the physical manifestations of that heat, watching it alter atmospheric dynamics to flatten the El Niño gradient.
We saw it strip the protective albedo from Swiss glaciers and push European infrastructure past its thermal limits.
Exactly. And we observed how those same thermal pressures are causing severe biological cascades, threatening microscopic glacial life, and driving unexpected local extinctions in temperate zones through shifting phenology.
We also examined the societal imperatives, analyzing how blunt, fragmented climate policies are systematically failing the 1.3 billion disabled people worldwide and ignoring the vital, localized knowledge of First Nations communities.
And finally, we looked at how humanity is fighting back through rigorous laboratory science, simulating permafrost to decode feedback loops, measuring hidden soil nutrients, and utilizing CRISPR to ensure our crops remain nutritious in a changing world.
And as we analyze these final innovations, it leaves us with a provocative, lingering question to consider.
What's that?
As we increasingly rely on artificial permafrost labs to understand our soil and CRISPR-edited crops to secure our basic nutrition against a hostile climate, are we slowly transitioning from being inhabitants of the natural world to becoming its perpetual engineers?
Wow.
What happens to our fundamental relationship with nature when our survival depends entirely on managing, simulating, and manipulating its every variable just to maintain an equilibrium?
That is a heavy thought to sit with. If the planetary X-ray machine is broken and the diagnostic landscape remains murky, it seems we are being forced to build entirely new tools to read the vital signs of the planet, and perhaps to artificially sustain them.
Indeed.
Thank you to you, our listener, for joining us on this deep dive today. Keep questioning the data, keep looking at the interconnected systems, and keep exploring the changing world around you.